am just so absolutely thrilled. I can't begin to tell you how thrilled I am. This is one of the really special days of the semester. I am just absolutely delighted to introduce Professor Brian Holmes. Uh, Professor Holmes, and correct me, I always do my biography off the top of my head, was a graduate of Pomona College.
Yep.
Then, okay, good. And traveled to the East Coast, went to Boston University, earned a PhD in physics. And while he was there, he was a horn player for the Boston Pops. He then came back to the West Coast and continued both pursuit of science and music. Is now an emeritus professor of physics at San Jose State. He was a professor of physics for many years. Also a horn player with San Jose Symphony, and has composed many pieces. Some of you who have sung in choir or jazz choir, I know any of you have ever sung in vivace would have done some of Professor Holmes' compositions. I was thrilled and excited to do it. I sang at Stanford when in the before times when we used to gather a choir in person. We'd have they'd get the old folks, the permanent community would come together for Christmas when all the students were gone, and we would sing. One of the things we would sing one of Professor Holmes' compositions. It was just so thrilling to have all of us come together. So he's here today to talk to us about the physics of brass instruments. There's all the other day we went back, talked a little bit about pipes. They did an example of woodwinds, and I'll just mention Professor Holmes. This is very interesting times for doing anything like this. I'm up in a chemistry room, so we have a fume hood in the back. So anybody who wants to try a brass instrument, a brass or a woodwind, they can blow into the fume hood and make the sound. So
My goodness,
we're still under pandemic restrictions, so it's a little unusual times, but we're having to we're doing the best we can with it. All right, so just to so yes, we hear you just fine. We hear and see you just fine.
I'm still not used to Zoom work. This talk I often give in crowded rooms and with a chance for people to interact. So some of my spiel relates to questions I ask, and I try to stop that now. But anyway, here's what I'm going to talk about. I'm going to talk about why brass musical instruments have their curious shapes, why there's a mouthpiece on the front end, why there's a lead pipe. It's a little hard to tell, but this section is conical, why there's a cylindrical midsection with valves, and why there's a flared bell, and why brass instruments develop that way. These shapes are pretty different from the shapes of woodwinds. If you consider the shape of a recorder, the recorder, though it's a little hard to tell from the outside, is essentially a long cylinder. It has this flare right here is false because it just simply is there for strength. But woodwind instruments tend to have very simple shapes. They're either cones or, like the recorder, a cylinder. So it's interesting why brass instruments developed with their complex shapes. And then a second issue is that when I started studying horn with Harry Shapiro in Boston, he said, stick your hand in the bell as far as it will go and leave about an inch of space between your palm and the side. So I'm going to talk about why horn players put their hands in the bell of the instrument. That's a matter of some historical interest. But let's make a start. And so where I'm going to start is not talking about sound at all, but let's see, what I want to do is, okay.
Oh, here we go, perfect, got it.
Okay.
Yes.
Well, this is a string. It's a string of beads, but it works just as well as a string. And I want to talk about, well, look, the central mystery of brass instruments is you may think that a trumpet is a device designed to put sound in a room. But in fact, the bell reflects sound that comes from the mouth and it reflects it back into the instrument. Only a tiny portion of the sound leaks out. And so I'm trying to develop an understanding of why sound reflects from the open end of a tube. At any rate, this isn't a tube, this is a string, and I could make a pulse and along this string, and we see that the pulse goes up to the clamped end and the pulse inverts. An interesting question is, why does this pulse invert? Let's do it in slow motion. So we stop for a second. When you see this upward pulse, the upward pulse pulls upward on the clamp. Now the clamp represents a node. It's a place where it's very difficult for the wave to move anything. And you can see as the pulse comes up to the clamp, the pulse pulls the clamp upward. Well, the clamp has a lot of inertia. It just stays there. And the string is pulling upward on the clamp over here. And it, as a result of Newton's third law, we see that the clamp is pulling downward on the string. Well, the clamp has a lot of inertia, but the string has less inertia. And because the clamp is pulling downward on the string, then a downward pull is exactly what you need to do in order to cause the pulse to invert. So that clamping effect reverses the polarity of the wave each time it encounters the end. So we see here in a case, we have two ends that are nodes, and each time the traveling wave encounters a node, it inverts. Well, that's pretty boring, but it's really easy to understand why a clamped end of a string inverts. Now, what I want to understand in a brass instrument is why we get the frequencies we do. So I'm going to start, and Greg, you've talked with them about strings, right?
Yes, we talked about strings and pipes both, but definitely that last time was a week ago, so a little refresher would be
okay. Well, that's
order.
fine. But I want to put this into my own jargon anyway. So
absolutely, yes.
what we're going to do is I'm going to oscillate this string, and I'm going to oscillate it at 40 cycles per second with a relatively low amplitude. And what we see, well, let me go back. How far does this wave have to go to repeat itself? If I make a big pulse like this, let's make a big pulse. Let's make a big pulse. There we are. So I make a pulse. How far does the wave have to go to repeat itself? Well, it's just traveled a distance L and it's inverted. It's traveling another distance L and now it's re-inverted. And we see, therefore, it has to travel a distance 2L in order to repeat itself. And the frequency, which is the repetition rate, has to do with this length. If the length were shorter, the frequency would be higher because the wave wouldn't have to go quite so far before it repeated itself. Now let's go and oscillate this thing. I'm going to oscillate with a fairly small amplitude, and I'm going to oscillate it at 40 cycles per second because I know what I'm doing. And I start it, and what we see is the oscillator is putting energy into this string, but you see after a while the energy builds up. The oscillator is sending pulses that go to the right and they reflect off to the left, inverted. And we see after a while we build up this form which is called a standing wave. We notice that the standing wave has got a node at one end, a node at the other, places which are pretty inactive, and in between the two nodes are places which are quite active, and we call those places antinodes. Now, when you study a physics book, you find something curious. The physics book says that a standing wave is the sum of waves going in opposite directions. But when I stare at this standing wave, I don't see waves traveling in opposite directions. But I want to show you that this frequency is the same as the frequency of repetition of that little traveling wave. And so let's see how I can do this. All right, we stop for a second. I reduce the amplitude to 0. And let's see if this, how this looks. Excellent. Now I've just made a little pulse that goes back and forth on top of this standing wave. And you can see that the repetition rate of the little pulse and the repetition rate of the standing wave are exactly the same. So the frequency is associated with a repetition distance of 2L. If you want to make a a higher frequency, you make a shorter string, or you make a tighter string that has a bigger velocity of the traveling pulse. Now there are other kinds of so that we call this particular standing wave, we call it the fundamental because it's the lowest frequency of this string. And what happens is we can, I have to explain some jargon right now. This whole shape right here, this arc, I'm going to call a hump. And at some point in our lives, we're going to start counting humps in standing waves. If I now shake this wave at twice the frequency, instead of 0.4 hertz, I'm going to shake it at 0.8 hertz. Let's see what pattern emerges. You can see I'm shaking it twice as fast. And as the wave builds up, it's no longer the fundamental, but instead we're getting a mode which is at twice the frequency. And if I freeze it, you can see now that there are two humps, a hump over here with a node in the center and a hump on the right. And by counting humps, we can figure out what the relative frequency is. And so now, for example, I'm going to shake this thing at, let's see, what's 3 times 40? 100, 1.2.
1.2, yeah.
Luckily, I don't have to get out my calculator to figure that out.
Good.
But sometimes in my engineering physics labs, I would ask a student what number they would get when they multiplied something by 10, and they would get out their calculator.
Yes.
It was disheartening. Now I'm shaking it at 3 times the frequency. And as the wave builds up, we see there's a new pattern. And the pattern, I hope, is one that Mr. Scott has shown you. And what we have here is 3 humps, and we have 3 times the frequency. And a bunch of frequencies that are integer multiples of the lowest frequency is a really important pattern in music. This pattern is called a sequence of natural harmonics, and it's really the basis of harmony. I want to show you. That's what I'm doing.
There you go. There you go.
All right. So I get out my ukulele, and of course I can get a higher frequency by shortening the string. But I can also get other modes by touching the string very lightly in the center. Could you hear it go up an octave?
Absolutely, yes.
But I'm not. I'm putting a node in the center so that the string oscillates in two segments like that. If I touch it 1/3 of the way along, you can hear that up at 3 times the frequency. And so we're getting a sequence of natural harmonics, the fundamental, the second harmonic, the third harmonic, the fourth harmonic. Well, can't hear it. I'm a horn player, not a ukulele player. Well, that was, that may have been interesting or may not have been interesting. I need to go back to share screen. And I want to go back to the wave on a string. There we are. Now what I propose to do is to unclamp the end, and it's going to be a loose end, and the far end is going to slide up and down on this. So instead of having, when a wave comes by and encounters the loose end, there's no longer the wave bound by the inertia of the clamp. And so when I send a pulse over there, let's send a nice large pulse. You can see the behavior is pretty different. You can see that the wave does not invert. Let's stop this and look at what's happening. As the wave goes up to the loose end, it shakes the loose end up, but notice that the loose end actually goes up much higher than the height of the original pulse. That's because there's so little inertia right here that the far end just continues much further than the individual segments of the string do when it's not bound at the end like that. I'm saying that very vaguely. But so the first question I ask is, when we have an unbound end like that, how far does this wave have to go to repeat itself? So we watch it. It travels it. So it just traveled a distance L. It hasn't repeated itself because it's uninverted, but when it encounters this nodal end right here, it inverts and So we see that it's traveled more than 3L. And finally, as it returns and it repeats itself, it's traveled at a distance of 4L. So we see there's a repetition distance of 4L. Well, that's twice the repetition distance we had when there were nodes at the two ends. And because the repetition distance is larger, well, then the repetition frequency will be much smaller. And when I shake this thing at a particular frequency, so I do this at a low amplitude. If I shake it at the old frequency, this is the old fundamental frequency. Of course, the old fundamental frequency had a node over at this spot. But when I just shake it at that old frequency, what we find is that no wave builds up. No wave builds up at all. Of course, I just tried to convince you that it had to be at half the frequency because the repetition distance was twice as much. And so now let's shake this thing at half the frequency. And you'll start to see that the wave builds up quite a lot of energy. And so we stop for a moment. How many humps are here? Well, this is actually half a hump. And that's really interesting because it's half a hump. Before, when we had an entire hump and nodes of the two ends, we had a certain frequency, and we had one hump, but now we have half a hump and it has half the frequency. Well, what other modes are allowed in this case? Well, we can also go to three times the fundamental. So we do that, we restart, we put in energy at 3 times the frequency. And you notice the energy is building up. And we have a new pattern. There's a node at the shaker end right here. There's another node right here, and there's an anti-node at the unclamped end. What we see here is 1.5 humps, or another way to put that is 3 halves of a hump. Since we started with half a hump, if we move to 3 halves of a hump, we have 3 times the frequency. We're getting natural harmonics, but they're not a full set of natural harmonics. A full set of natural harmonics would have all multiples of the lowest frequency. If we shake this thing at 5 times the fundamental frequency, then we get yet another pattern. And what you see right here is 2.5 humps. That's 5 halves of a hump. We went from 1 half to 3 halves to 5 halves. And in doing so, we went from 1 unit of frequency to 3 units of frequency to 5 units of frequency. I would say the most important musical interval is the octave. That's what happens when, well, here's an octave. That's a doubling of frequency. Doublings of frequencies are pretty important in music. In fact, octaves are notes which are so similar that we give them the same name. We say middle C and high C. We don't rename the C because there's some sense in which its character mimics the character of the lower note. So octaves are pretty important. But in this situation where we have a node at one end and an anti-node at the other, we never get octaves. I'm going to show you that when I build a trumpet and I start with a long straight tube, that I can't get any octaves out of that tube because the tube has got a node at one end and an anti-node at the other. But of course that's sound, and this is a string. So I think we're done with the string. So we stop sharing. And I magically reappear in my cabin. I had a little studio built in my backyard so I can write music here whenever I feel like it. So in my mindless way, I've decided to build a trumpet. And what you see right here is a long piece of tubing. Now it looks like a mouthpiece on that end. That's just simply the rim of a horn mouthpiece, because if I were to blow on this tube without that rim, then it would wreck my embouchure. Perhaps you don't know what an embouchure is. When I started studying horn with Harry Shapiro, I had a lip. After 2 years of study, I had an embouchure, which is the proper way for lips to act in a brass instrument. By the way, the English language does us a tremendous disfavor when it says, Gabriel, blow the trumpet. Unfortunately, if Gabriel were to actually blow a trumpet, nothing would happen. You don't blow a brass instrument. You have to there's my embouchure, and you have to buzz it. You have to put sound into a brass instrument in order for it to function. And so what I have here is this tube. It's 141 centimeters long, and that happens to be the actual length of a trumpet without any valves down. And what I propose to do is to buzz into it. I have to back up a little bit. There we are. So I will now buzz into it. That's kind of interesting. Although I can buzz my lips at any frequency I like, when I do so into the tube, it selects certain notes. How does that happen? Well, since I don't understand how it happens, I go to my physics book, the source of all reasonable knowledge. And what we discover is that when sound goes down a tube and encounters an open end, the sound reflects and stays inside. Now, to my mind, that's a very difficult thing to understand. If you were to look at an open door and throw baseballs at an open door, you would find that none of them would reflect from the open door and stay inside the room, that all of them would travel through the door. And yet sound traveling down a tube, when it encounters an end, most of the energy stays inside. In fact, in a trumpet, about only 2% of the energy leaks outside. The other 98% of the energy reflects from the bell, stays inside the tube, and returns to the lips. So the next thing I want to do is to try to explain why sound inside a tube reflects. Now, unfortunately, I like to do this with a skit, and we can't do the skit. So I will wave my hands and we will see what will happen. What is sound? Sound is a bunch of pressure variations in the air. We can have high pressures, or which are called compressions, or low pressures, which are called rarefactions. I don't like to think of air as being a bunch of molecules. That's not a productive way to think about sound. Sound travels at 340 meters per second, which is pretty fast. But if you look at the individual molecules, you'll find that molecule right there is going about 400 meters per second. And it doesn't travel very far before it hits another molecule. The motion of individual molecules is very jaggedy and very irregular. But what about sound? So the individual molecules are going hundreds of meters per second. But when sound comes by, the air moves back and forth no more than about 1 millimeter per second. This is a very small velocity. In other words, this is superposed on top of the individual chaotic motions of the molecules. So I think it's better to think in terms of chunks of air. We take a chunk of air right here, and we average over all the molecules so we don't worry about the thermal agitation. And then when sound goes by, it causes very tiny motions.
Okay.
Because if dots were showing what the actual molecules were doing, then those molecules would be diffusing throughout.
Okay, yeah, it shows a little bit of the chaotic motion, but not quite to the extent.
But you understand that when so understand that when the chunks of air get closer together, we build up a compression, and when chunks of air get further apart, we end up with a rarefaction.
Yes. Now
let's take a bunch of air. There it is, right there. And what I propose to do is to compress it. Excellent. Now what I propose to do is to release it. What happens? Well, if we release it, well, then the air starts to expand outward because it's at high pressure. And as it expands outward, the pressure will fall until at some future moment, it will be at 1 atmosphere. Does the air stop moving at that point? No, because the air has been moving. The first law of motion tells you that an object in motion continues in motion. So the chunk of air will continue to expand until there's a low pressure inside, and then it will stop expanding and it will recompress. In other words, if you just put a high pressure in a room, it doesn't simply expand until it gets to 1 atmosphere. Instead, it expands much further because of the inertia of the air. Now we have to imagine, let's imagine that we have right here a tube, okay? And here's one chunk of air, And here's another chunk of air. And what I propose to do is to move these chunks of air closer together. So I'm going to move this chunk over here until it's close to the one over here. Now, because I've moved them close together, this chunk of air will be pushed off to the side. And so now, is that what would happen in a room? In a room, if I was to build up a pressure like that, why then the air, instead of just simply going in one direction, would expand in all directions. Because that's the way sound moves in a room. It expands, the high pressure will expand in all directions. But in a tube with rigid walls, why then if I have a high pressure region, why then the only response for the chunks of air is to move along the tube. Now, you see, therefore, that the motions of chunks of air in a tube when sound goes by are different from the motions of chunks of air in a room when you have sound. Because in a room, the chunks of air can expand in all directions, but in a tube, they can only expand along the axis because of the rigidity of the walls. This suggests that when we push a chunk of air at the end of the tube, the behavior is kind of different. So here are two chunks of air in a tube. And when I push this chunk right in this direction, this chunk can only move in that direction. But now let's pretend that this chunk right here is at the end of a tube. Then when I push on it, as I push it out of the tube, it can actually expand in all directions. There's no pressure building up on the other side of it to cause it to stop. And so it goes extra far. And as it goes extra far, why then a rarefaction develops between the two chunks. So we review what's happening right here. By the way, I'm finding this very difficult because the camera is reversing, the camera is not acting like a mirror. So I'm having, so at any rate.
And you have an option with the video to reflect, you can have it mirror your image if you wish.
Yeah.
I'll leave it. But
let's not worry about that right now.
Not a problem, not a problem.
I'm almost done. So here's what happens then. We have two chunks of air, and this is the chunk of air at the end of a tube. As I move this, as a chunk moves towards this one, as a high pressure impinges, this one moves out, but no high pressure builds up on the other side because the air is just scooting out of the way. It's moving in all directions. And so the chunk of air at the end of the tube moves extra far. As it moves extra far in this zone in between, a rarefaction develops, and therefore the rarefaction, the high pressure wave has been turned into a rarefaction, and that rarefaction is what goes back up the tube. This should remind you of that string that I showed you when the string end was clamped and I made an upward pulse on the string and it encountered the clamped end, it inverted. In the same sense, the pressure wave inverts as it encounters the open end of a tube. And therefore the open end of a tube is going to be a pressure node. Now, what would happen if you had a wall at the end of a tube? Here's a wall at the end of a tube, okay? If a high pressure region comes up to there, it cannot cause the wall to move, and so that high pressure region just simply bounces off. And so a high pressure region takes whatever character of the sound wave, a high pressure, for example, and it bounces it right back off. That should remind you of the unclamped end of the string. The unclamped end of the string would take an upward pulse and it would reflect it as an upward pulse. And that was an antinode. So we see that the open end of a tube is a pressure node, and the closed end of a tube is a pressure antinode. A question for Mr. Scott: how do you also teach sound as being displacements of chunks of air, or do you limit yourself to pressure variations?
I've shown them both ways. Generally, we talk about displacement of chunks of air when we talk about the pipe waves. But I did say that there are both, but primarily when we draw our pictures, we show the displacement.
Displacement is a little easier to understand because it's very easy to displace chunks of air at the end of a tube. And so with respect to displacement, the end of a tube is a displacement antinode. But if you have a wall and you try to displace chunks of air by it, you can't. The chunks of air just simply bounce off. And so displacement is 0 at the wall end of a tube. In any rate, whichever character you assign to sound, the open end of a tube is a pressure node or displacement antinode, and a closed end is the reverse of that. Now that's what's happening here. I can buzz my lips at any frequency I like, but when I buzz them into the tube, it only buzzes at certain frequencies. Why is that? Well, as I buzz my lips emit high and low pressure puffs of air. Those high and low pressure puffs of air come up to the end of the tube, and they are inverted, turned into low and high pressure puffs of air, which return back up the tube. And therefore, my lip is being bombarded by reflected pulses of air, which are high and low pressure puffs. And those puffs, those high and low pressure regions interact with my lips. Suppose, for example, that a high pressure region encounters my lips. It will open them further and be reinforced by more air from my mouth. But suppose a low pressure region encounters my lips. Why, then it will close the lips down, and therefore there will be not that reinforcement. And so you see that the returning pulses are offering feedback to my lips and controlling their frequencies. And you can hear what happens inside this tube. You can hear what happens to the sound if I try to gradually raise the frequency of my lips. If I do that into the tube, you hear that instead of going gradually, it just simply goes from one mode to another. It's possible for me to buzz my lips at a frequency between the modes, but it's very difficult because I can't rely on the control offered by the tube. Instead, I have to have all the control out of the muscles of my embouchure. So this is, so now we can try to understand why doesn't this thing sound like a trumpet? Well, let's listen to it again. Well, it doesn't sound like a trumpet because number one, it's kind of out of tune. Of course, some trumpet players do play out of tune, but that's not what I mean. For example, this is a tube which is open at this end and it's closed at that end by my lips. So it ought to be getting odd multiples of the lowest frequency. I'm not going to put up the frequencies for you to look at, but I'll simply show you that I can't make any octaves. After all, in a sequence of odd integers, there is no integer which is going to be twice the frequency of another. So if I go, there's no octaves there. And I'm getting simply a bunch of odd multiples of the lowest frequency. The other thing to notice here is that some of these notes I can bend. Why can I bend them if I'm getting feedback from the tube? Well, think of this. How much inertia do my lips have? Quite a lot compared to the amount of inertia that the air has. And so at some frequencies, the notes are quite bendable. The feedback is imperfect. But of course, that doesn't really explain how a trumpet works. So let's advance further. On the front end of a trumpet, what you have is a trumpet bell. And I can put this bell on without actually changing the length of the tube. Let's see if I can show you. This cylindrical tube and this bell have the same length. But interestingly, they have different acoustical properties. The first thing you would expect is that you would expect to get more sound out of a flared bell like this than you would out of a tube. Why is that? Let's ponder the fate of a high pressure region moving along this tube. The high pressure region moves along the tube, it moves, and all of a sudden it encounters this end. Now the high pressure region here inside the tube is confined to a very tiny region. But out in the room, that high pressure region has to suddenly become a sphere and expand in all directions. That's a big change to make in a very tiny space. And that big change in the tiny space explains why there's so much of the energy reflected and stays inside the tube. But that also explains why we expect for the sound in the bell to be louder. Why? Let's follow the course of a high pressure region along the tube. Here it's confined in a narrow region. Now, as it moves along, the region where it's confined expands. So the high pressure region is now crossing a much larger region. By the time the high pressure region encounters the end of the tube, the high pressure region is pretty large. Now it's not room size, but it's larger than it was when it was at the end of this tube. And therefore the flare helps to make a gradual transition from tube-like behavior to room-like behavior. And as a result, we expect to get more sound into the room. And so let's test this notion. We'll go back to the tube. And let's see if we get more sound when we put the bell on. I hope I've convinced you that I got more sound out of it. I wasn't actually blowing any harder, but I hope that you noticed that the frequencies changed. Let's go back to this low frequency right here. Let's hear how that one changes. Let's hear how it changes when we put the bell on. That's a whole step, okay? Whereas if I go to this higher note right here, now let's put the bell on. You can hear it was also raised, but it wasn't raised as much. That lower note was raised by about 15%. That upper note was raised by about 3%. Now, what's the simplest way to raise the frequency in a musical system? Well, this is a way which is so simple that it's well known even to guitar players. You shorten the string and you get a higher frequency. Now, in a tube, we can shorten the tube to get a higher frequency. But the interesting point of this demonstration here is that we did not shorten the tube. The tube was not changed in length by replacing this segment with a bell. So what's going on? Why are the frequencies raised? Well, the answer is the acoustical end of the tube is no longer the actual end. If a certain note was raised by 15%, then it didn't reflect at the bell. It reflected 15% of the way in. And we saw that the lower notes were raised far more than the higher notes. So the lower notes reflect before they ever get to the far end, and they reflect in the narrow throat of the bell. As we move to higher frequencies, the modes reflect from closer and closer to the end of the bell. And so we see that this system is all of a sudden what we call nonlinear. Its reflection point depends on what the frequency is. And that helps to change all the frequencies. I think you can hear that we get a slightly more musical result out of it. It's still not quite musical, but you can hear that the notes have been shifted in such a way that they are more recognizably part of a harmonic series than they were before. Not quite yet. Now this has, here's possibly the most difficult idea I plan to present. If low frequency notes reflect in the narrow throat of the bell, and higher frequency notes reflect closer to the end of the bell, then that means that the bell is transmitting more high frequency sound into the room than low frequency sound. It's like a high pass filter. A high pass filter takes a bunch of signals and it lets the high frequencies through and keeps the low frequencies back. A bell is like turning up the treble knob on a stereo. You get more high, you can hear the flutes better. But it also has the following interesting implication. If low frequency notes reflect in the narrow throat and higher frequencies reflect further out, what if we move to even higher frequencies still? If we move to higher frequencies, we discover that above a certain frequency, we get no reflection at all. This is very curious. If there's no reflection at all, that would suggest that all the sound at that frequency is going into the room. But that's not desirable. If all the sound is going into the room, then none of it is returning back up the tube to the lips, and there's no longer any control. I'm going to show you that a French horn is played above the cutoff frequency of the bell for certain notes. Now, what is it? And that's one of the reasons. Well, I can show you that right now. Here's my horn. I'm going to keep the hand out of the bell. Listen to these notes I play. You can hear how the horn is controlling my lips, and it's selecting certain notes that I play. I can't play in between. Now listen to what happens as I go higher. You can hear all of a sudden it screeches continuously from one frequency to another without any control. All the sound is going into the room, but that's not desirable. It makes it very difficult to play high notes. But when I put my hand back in the bell, all of a sudden I get restore resonances in the high register. So listen to this again. Now I put the hand in. So what the hand does in the horn is it restores resonances above the cutoff frequency. And this makes it easier to play high notes. And it also improves the tone quality of lower notes, which may have harmonics above the cutoff frequency. That's why I like to talk about cutoff frequency. Cutoff frequency matters in various brass instruments. A trumpet with a very rapidly flared bell has a high cutoff frequency. That means it delivers a lot of high frequency information into the room. If, however, my flugelhorn, a flugelhorn has a much more gradual flare, and the gradual flare is associated with a lower cutoff frequency. Listen to the tone quality. You hear it's not quite so edgy. The edginess has to do with the fact that this bell, with its lower cutoff frequency, is delivering more low frequency sound into the room. And that darker sound has to do with the fact that the low frequencies are more prominent in the spectrum compared to the high frequencies. So that accounts for some differences among various brass instruments. Now let's see. Oh yes, at the that's the bell. At the close end of the trumpet, well, before I had this cylindrical lead pipe, but in an actual trumpet, what you have is a mouthpiece, and I can't remove this mouthpiece, but this is what the mouthpiece looks like. It has a hemispherical cup to it. The cup has got a hole at the bottom, and then along here, you can't see it, but in fact, the airway is expanding as it goes from the narrow throat to the cylindrical tube. And then what we have is we have a lead pipe, and the lead pipe continues that expansion until there's a gradual transition from the very small back bore of the mouthpiece to this cylindrical section. What does the mouthpiece do? I can buzz my lips at any frequency I like. In fact, you find that I often do buzz my lips at any frequency I like. But if I buzz my lips into a mouthpiece, I get an interesting result. What goes on is that a mouthpiece acts like a Coke bottle. Do we in this generation know what a Coke bottle is? I know this is I'm not allowed to mention beer bottles, but there's a phenomenon which is known to people who will explain it to you in case they've done it. If you blow over the top of a bottle, you hear a certain hooting sound. And this hooting sound gets lower in frequency the more air there is at the top of the fluid. And the mouthpiece, in fact, is like we see here a little cavity right here, and that has a certain natural frequency the same way that a bottle does. And I can cause you to hear this frequency. Here I have a trumpet mouthpiece, and here I have a trombone mouthpiece. I will now pop them against my palm and listen to the difference in the sound. You can hear that the popping frequency of the trombone mouthpiece is lower than the popping frequency of the trumpet mouthpiece. The popping frequency of your typical trumpet mouthpiece is about 600 cycles per second. So what's going on right here is when I go, there's lots of frequencies there. When I go, the difference is that there's more energy at 600 cycles per second when I buzz into the mouthpiece. And that 600 cycles per second, where is 600 cycles per second? Yeah, it's right about up here, about high G. Maybe that's close enough. In other words, what this does is it amplifies certain sounds. Now, if I buzz into the trombone mouthpiece, it's a milder sound because it's amplifying at lower frequencies. And so when I use the trumpet mouthpiece, I expect a certain stridency, which comes of the amplification of sound near the popping frequency. And we can hear this. Here's the straight tube. You can hear that with the mouthpiece. It's a lot edgier. But I hope you also heard that the frequency rose. Let's test this again. Here's another mode. That one's quite edgy, but also the frequency again rose. In other words, now these two tubes have the same physical length, but the acoustical length of the mouthpiece and lead pipe is actually shorter than the actual length. And so what this does is what the mouthpiece does is it adds stridency to the tone, depending on the popping frequency, and it raises the frequencies. So what happens when we put this thing on? Is we get this result. And you see that this instrument has become convincingly a trumpet. We now are getting resonances at a sequence of natural harmonics. Pause for a moment. This ends at 9.
We actually go till 9:15, so
okay. That's good.
Okay.
So I can monitor and just say things at great length. I'll try to leave time for questions.
Please. Okay.
Notice that we're getting a full sequence of natural harmonics. I can get octaves now. And so the bell and the mouthpiece and lead pipe have contrived that the instrument is producing a sequence of natural harmonics, whereas when it was just a long cylindrical tube, it wasn't doing that. And that turns out to be highly desirable behavior. Suppose I play a note like this. That note is feeding back information to my lips and controlling it at that particular frequency. But understand that any complex musical sound has harmonics to it. And the second harmonic of that frequency is up here, and that also is a resonance of the instrument. And therefore, not only is the fundamental of the note I'm playing feeding back information to my lips, but the second harmonic of the note I'm playing is also feeding back information to my lips, and also the third harmonic, which is way up here. And so what we have is a collaboration among all the harmonics, which are all feeding back information to my lips, and all of a sudden the notes are very definite. As a player, I find it's very difficult to shift the frequencies of the notes away from the resonances. Here, I'm going to try to move a note flat with my lips. Let's listen to what happens as the instrument controls my lips. You can hear that I can play slightly flat, but it's very difficult. The instrument is so controlling of my lips that basically I have, as I buzz my lips, I have to agree with the frequency that the instrument wants me to play at. Now there are exceptions. There still is a note down here. Which is not related. Why is that? Well, remember that low frequency notes reflect in the narrow throat of the bell. But in order for that note to be in tune, the bell should have started much sooner. And so that note is left out of the family of resonances, which are a harmonic series. By the way, that has nothing to do with the fact that this instrument is a long, straight instrument, and a trumpet is all bent on itself. I get the same notes out of a trumpet. And so that has nothing to do with the fact that this has been rendered more compact. These things should help you understand why trumpets have valves. What does a valve do? Well, a valve, let's consider the second valve, for example. When I push down the second valve, why then the sound goes through this detour right here. And this detour actually happens to be about 6% of the length of the instrument. So since the distance between the mouthpiece and the bell has been increased by about 6%, the frequency falls by 6%. I can get a certain pattern of notes. And I can get the same pattern lowered by 6% by pushing the second valve. The other valves, for example, the first valve is about 12%. So instead of being content with playing bugle calls, I can get the notes in between. Couldn't you get the same result by putting holes in the side of the instrument the way you do in a woodwind? After all, when you play a recorder, you can hear what I'm doing is I'm lifting my fingers. As I lift my fingers, why then the instrument, instead of being terminated down here, is terminated by the first hole. And that means that the distance between the open hole right here, called the fipple, and the next open hole downstream has been shortened, therefore the frequency rises. Couldn't you use the same scheme for a trumpet? Well, you could. What I propose to do is to remove this second valve tuning slide, which I've now lost on the floor. And what's going to happen is when I push the second valve, instead of the music going round and round and coming out the bell, the music is going to come out a hole in the side right over here. So let's listen. You can hear that the sound has a very different character. After all, I've shortened the instrument, but more important, I've taken the bell off. And the bell was an important feature of the instrument for processing the way the instrument sounds. And so these notes are no longer have a harmonic relationship to each other. And the tone quality is pretty different. So I would imagine that if you had a trumpet with holes in the side, that the open notes and the notes played with holes in the side would sound pretty different. They might sound like this. Well, listen to that bending. That's a sign that when the sound bounces off the hole, it's not producing as much control of my lips. And so I can bend the notes more. Now that may be so, but in fact, brass instruments were made with holes in the side. I show you this wonderful object. It has a flared bell. It has a mouthpiece, but it's not a trumpet. It doesn't have a trumpet-like shape. A trumpet, after all, is mostly cylindrical, and then it's flared at the end. This instrument, however, is conical. Its flare starts right here, and it continues gradually throughout the entire length of the instrument, like that. And so let's listen to what happens as I open holes in the side. Now I'm going to open holes in the side. You can hear, in fact, that the sound is fairly uniform. Why is that? I thought I just convinced you that you couldn't put holes in the side of a trumpet. Well, this is not a trumpet. If you put a hole in the side of a cone, it's still a cone. You put a hole in the side of a trumpet, and you've taken the bell off. And so there's a difference between English and American English. This instrument is called a keyed bugle. The keys are these openings in the side. And the word bugle comes from the fact that this instrument has a conical profile. Now, in American English, we use the word bugle to denote any valveless trumpet. But in fact, a trumpet has a flared bell right at the end, whereas a true bugle is conical throughout its entire length. If you understand this distinction, then you'll understand that of all the orchestra instruments, the tuba is most nearly a bugle because it's conical throughout its entire length, whereas the trumpets and the trombones, and to a certain extent the horns, are more flared towards the end. This particular instrument was made about 1835. The keyed bugle was invented before the invention of the valve, and this was the principal soprano brass instrument in the military band from about the time of Napoleon to about the beginning of the American Civil War. Here's a tune from the Civil War. I won't go any further. That's Kingdom Coming by Henry Clay Work, a wonderful song. And a song we don't hear sung very often because the composer imagined that the song was sung by recently liberated enslaved people. And unfortunately, the language in the song is not language we care to listen to these days, but it's a wonderful tune. Now it's interesting, this instrument has a very gradual flare to it, and that means it has a low cutoff frequency, and that's why this instrument doesn't sound very edgy. It has this wonderful sweet sound to it. When valve trumpets came in, being trumpets, why then they were flared a lot towards the end. And being flared a lot towards the end, they didn't have a very mild sound. Here I will attempt to serenade my youngster. That's wonderful. The kid will fall asleep right away, but if I try to do that with a trumpet, I get a somewhat different response out of the child. Oops. I forgot my second valve tuning slide. There we are. You can hear that the trumpet with its flared bell and its high cutoff frequency makes a very strident sound. When keyed bugle players were forced by their bandmasters to switch to the trumpet, they said, "Ooh, it sounds really harsh and strident. Can't you give us something with a bigger bell, more like the bell of a keyed bugle?" And that's how the cornet came to be invented. Now, these days, cornet players sometimes are careless and they play their instruments with trumpet mouthpieces, and so they still sound strident. But that's why there's really two kinds of trumpets. The flugelhorn is kind of different, but it's even milder sounding than a cornet. So that's why valves work on brass instruments. It's very difficult to put holes in the side of a trumpet because that takes the bell off the instrument and it changes the tone quality considerably. What I propose to do now is to show you one of my horns. This is not a hunting horn. This is a, I call it a natural horn. The word natural just means it has no valves. It has a mouthpiece and a lead pipe, but this piece of plumbing that you see right here is called a crook. It's a piece of tubing which is just the right length so I can play music in the key of F. The instrument has quite a small cylindrical section, and then it has a rather long bell. I can get all these notes. Again, I'm doing this all with my lips. I'm keeping my hand in the same spot. There's quite a lot of notes there. And in the Baroque time, composers like Bach or Handel would have players, the instruments were more like hunting horns. They had smaller bells, they had shallower mouthpieces, and they were played with the bell up. So I'm just relying on notes of the harmonic series. The harmonic series, though, is not quite in tune. Listen to how I continue that tune. So the harmonic series doesn't quite do it. It's a bit of a mystery how Baroque trumpet players and horn players were actually able to play their instruments in tune. I will spare you that argument, but I want to show you something that happens as we go back. Here's an organ pipe. The organ pipe has an opening right here and it has an opening right there. And because there's two openings, there's nodes at the two ends, and there's a fundamental frequency. I can get twice the frequency by blowing harder. But if I put my hand over the end, I convert this end from being a pressure node to being a pressure antinode. The repetition distance doubles and the frequency becomes half as much. That same phenomenon is observed in the horn. And as I insinuate my hand in the bell, I lower the frequencies of the notes. But I want you to notice that when I lower the frequencies, I'm lowering the frequencies of the low notes more than I lower the frequencies of the high notes. So what's going on here is I'm converting this open end from being a pressure node to being a pressure antinode. As I do that, the frequency falls. And instead of being content with playing the notes of the harmonic series, I can get all the notes in between by adjusting the position of my hand. That's the technique which Mozart and Beethoven expected their horn players to play. Actually, that's the technique they expected their soloists to use. The orchestra players at the time were not nearly so skilled. But here is, for example, the opening of Beethoven's Horn Sonata. Now, I hope you notice that I'm playing with my hand in the bell, even for the open notes. It would be very awkward if I had to move my hand in and out of the bell like this. And so the hand is kept in the bell, even for the open notes, to give them more of the muffled character that the covered notes have. And then I also don't play loudly. If I play loudly, then the covered character of the notes diverges from the open notes. If I play more quietly, that covered note still has a special character to it, but it doesn't diverge so strongly from the character of the open notes. And so the hands entered the bell to allow players to get notes that weren't part of the harmonic series. As this happened, then the bell was made larger to accommodate the presence of the hand. The mouthpiece was made shallower so as to make it, was made deeper so that the instrument had more energy at low frequencies, and the instrument became darker in character and slightly more muffled in sound. If you listen to the modern horn, you might think that the modern horn, with all of its special all its special valves and stuff, wouldn't require the presence of the hand. After all, the hand is no longer active. But I've already shown you that the hand restores resonances above the cutoff frequency. So as I play in this high register, it's much easier to play those notes. But even if I play in the low register, the tone quality is affected by the presence of the hand because those low notes may have harmonics above the cutoff frequency. Let's play a tune and see if you can hear the difference with the hand in the bell and the hand out of the bell. I don't know if you can hear much difference. As a player, I noticed two things. Number one, that the sound quality is a bit more blatty sounding. It's a bit fuzzier sounding. The notes aren't quite as clear. The other thing I noticed as a player, that the control offered by the horn to my lips is not as strong. And so I have to work a little bit harder to play those notes. So that the hand remains in the bell so that the hand can restore resonances above the cutoff frequency. But also the hand is useful in case I want to, you remember that when I put the hand in all the way, it diverged in character. That's actually a special muting effect. Here's a solo from a piece by Rimsky-Korsakov. You certainly wouldn't be timed to put in a mute for that, but because the hand is there and because it changed the quality, then composers often expect that. Here, for example, is a solo I wrote. All in green went my love riding into a silver dawn. 4 lean hounds crouched low and smiling. This is a poem by E. Cummings. And the tune is 4 lean hounds crouched low and smiling. But here's how the horns play it. Of course, generally they play it better than I just played it. But the sinister nature of the hounds is brought out by the rapid change in tone quality caused by using the hand in the bell like that. So that's a special muting effect that players use. Also, I can adjust the intonation of the instrument. If I want to play a certain note a little bit flat, all I have to do is move my hand in a little bit. And so I can adjust the pitch of the instrument without actually changing the length of the tuning slide. And that's what horn players do with their right hands. And I wonder if there are any questions, because I'm done. I can always talk more.
Okay.
All right.
We can go about 3 more minutes. I think we could do that if you want.
This is a shorty. What do you call this instrument? I always called it horn, but some people call it French horn. Actually, English is the only language where the instrument is called French horn, and it has nothing to do with French. After all, in France, they simply call the instrument cor, which is horn. And so why do we call the instrument French horn? The answer is the hunting horn that the French used wrapped around the player's body and was used for hunting deer. And that was quite a long instrument, and it produced hunting calls like this. Why do you need to play a horn while you're deer hunting? Because the forest is thick and you can't see the deer, but maybe somebody else can. And when they see the deer, they make a signal to let you know what the stage of the hunt is. Now, the English did not hunt deer, they hunted fox when they weren't hunting the French. And this is the kind of horn they used. It only produced one note, which could be bent. And so they communicated the stages of the fox hunt, but with a series of sort of Morse codes. Like that. When instrument makers in London started making horns, hunting horns, why they had to differentiate between the French style hunting horn, and so they called them French horns, whereas this was simply called horn, because that was a true hunting horn. However, it's my unfortunate duty to tell you that this hunting horn was made in Pakistan, so maybe it's a Pakistani horn. Anyway, that's why the instrument is called French horn, and why true horn players who belong to the International Horn Society never call the instrument French horn.
Okay.
That's a form of arrogance.
Very good. Much appreciated. All right. So again, a huge thank you to Professor Holmes for sharing his expertise and your talent and all your knowledge with us today. It's
You're welcome.
Really makes a very, very special day for all of us.